Good morning. Today we're going over our second homework assignment for nuclear chemistry, and hopefully you'll find that this one is just as easy as the last one that we did. First, we're looking at fission and fusion as two additional types of nuclear reactions. And they did explain over here that fission occurs when you have a nuclei that falls apart, and that's usually something that's really heavy. And fusion is when you have smaller nuclei that join together. And so for part A, where they say, what do you think would be used in a nuclear fission power plant? Well, the bigger nuclei are going to be there. So the biggest one we've got is uranium-235. That's the one that's going to be used there. And what's going to be the best for nuclear fusion? You want something smaller. Smaller nuclei undergo nuclear fusion best. And characterize these as fission or fusion. They both release lots of energy. Fusion occurs in the sun, and it needs very high temperatures, which is why it occurs in the sun, and it needs very high temperatures. The fission is where you've got byproducts with really long half-lives, and that's what's used in nuclear power plants. And these reactions are going to be exactly like the ones that we have done previously, where your mass has to add up and your nuclear charge has to add up. So the isotope that's being formed, 238 equals 234 plus 4, and 92 equals 90 plus 2, and the element number 2 is helium. In this case, 234 equals 234 plus 0, and 90 equals 91 plus a negative 1. So element number 91, if we bring up our periodic table here, 91 is right here, protactinium, Pa. And now, whatever's on the left still has to equal that which is on the right. So 222 plus 4 is 226. And 86 plus 2 is 88. And element number 88 is radium. And again, some of these are fusion and they have some other byproducts, so they start to get more complicated, but it's just as simple as all of the mass on the left has to equal all the mass on the right, and all the nuclear charges on the left have to equal all the nuclear charges on the right. So 14 plus 4, total mass of 18 on the left. Something plus 1 must equal 18, so that's going to be a mass of 17. 7 plus 2 gives me a nuclear charge of 9 on the left. It's going to be 8 plus 1 to give me a total of 9. And element number 8 is oxygen. (27 plus 4 is 31. So that's going to equal 30 plus 1. 13 plus 2 is 15. 15 equals 14 plus 1. Which particle has a mass of 1 and a charge of 1? That's a hydrogen. 235 plus 1 is 236. Gonna need a calculator for this one. 236 on the left. On the right, I've got 90, and then there's 3 neutrons. So 90 plus 3. So I've got 93 mass represented here. So this has to be the rest of that. So 236 minus 93 means the remaining mass must be 143. And then I've got 92 plus 0 is 92 on the left, minus 38 plus 0 is 38 on the right. And I get atomic charge of 54. Element number 54 is xenon. Something plus 4 is 113. That should be 109. Something plus 2 is 49. That should be 47. Element 47 is silver. Something plus 4 equals 13 plus 1. 13 plus 1 is 14, so 10 plus 4 is 14. And 7 equals something plus 2, that's going to be 5. Element number 5 is boron. Now they want the whole nuclear equation of what's happening here. Tells us we've got uranium-238 captures a neutron, so we're adding a neutron, and then it emits, that is, releases, it has a product, 2 beta particles to make the plutonium. So uranium-238, uranium is 92, captures a neutron. Neutrons, 1 mass, 0 nuclear charge, go to form 2 beta particles, and beta particles are electrons. They have a mass of 0 and a charge of -1, and says a fissionable isotope of plutonium. If we did this right, that's what we should get. 238 plus 1 should be 239 plus 0. 92 plus 0 is 92. That's going to equal -1 plus 93. I'm sorry, there's 2 electrons there, so that's going to be 94, right? 94 minus 2. That's plutonium. Indeed, that's what they told us that we would be making. What is the parent isotope of this decay series? Bismuth-212 is used for stuff. It is formed after the parent isotope undergoes a decay series consisting of 4 alpha decays and 1 beta decay. So I've got some parent, I don't know what it is, and it goes to form bismuth-212, right there, 21283. And it tells me that it also makes 4 alpha particles and 1 beta particle as part of this decay series. So alpha particles look like this, and beta particles look like this. And they want to know, what did I start with? So 212 plus 4 times 4 is 16. Plus 0 gives me a mass of 228. And then at the bottom we have, this number has to equal 83, plus 4 times 2 is 8, plus -1. So it's going to be number 90. And element number 90 is thorium. Now, they don't want the whole equation. They just want to know what the parent isotope was. I just wrote out the whole equation so you could see how we got there. But they said, when the parent isotope decays, this is what you get out of it. So when I was able to construct the rest of this, it was easy to calculate that thorium is what they wanted. All right. Meitnerium was prepared by the bombardment of bismuth-209 with iron-58. They want the balanced equation, so let's put that here. 266, 109. Now that was prepared, so that's the product. And that came from bismuth-209. Bismuth is 83. And iron 58. There's iron, element 26. Now Now it does say there was another product formed. We can do the math. 209 plus 58 gives me 267. If I got my nerium 266, then I've got a mass of 1 unaccounted for. I better include that. And 83 plus 26 gives me 109. Meitnerium 109 means this must have a nuclear charge of 0. Which particle has a mass of 1 but no charge? That is a neutron. So that is the whole nuclear equation. And the other product formed was the neutron. This problem was easier to do in reverse. So next we've got a few questions on half-life. And we're going to start with this one. Phosphorus 32 has a half-life of 14 days. If I start with 2 grams, how many will remain after 56 days? Now the problems that I give you here are going to be relatively simple in that they have whole numbers of half-lives. So the first thing you're going to do is say, well, how many half-lives have passed? 56 days is fine, but that's not as interesting as saying how many half-lives is that? So 56 days divided by 14 days and a half-life gives me 4 half-lives. And this is actually, you could look at this as dimensional analysis. 56 days. Here they told you 1 half-life equals 14 days. So 14 days and a half-life. Days cancel and we get 4 half-lives. So your original amount is going to be cut in half 4 times. So we start with 2 grams and we cut it in half. Once, twice, 3 times, 4 times. We get 0.125 grams. Next, carbon-14 has a half-life of 5730 years. And if we find that it has decayed to 1/32 of the original amount, that's the fraction that remains, not the amount, but the fraction. So 1/32 is going to be 1/2. See, 1/32 is 0.03125. We want to know how many times I have to take my original 100% and divide by 2 to get that much, that fraction. Here's 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, 5 half-lives. Took me 5 half-lives to get to 0.03125. So 5 half-lives means 5 times 5730 years. That's 28,650. Now fluorine-18 has a half-life of 110 minutes. And if they shipped it at 8 a.m., they want to know how much is left at 1:30. So first we have to calculate how much time is that. So from 8 a.m. to 9 a.m., 10, 11, 12, 1 p.m., that's 5 hours, plus another 30 minutes. So 5 hours times 60 minutes, plus another 30 minutes, that's 330 minutes have passed. Divide by a half-life of 110 minutes, and we see that 3 half-lives have passed. So if I started with 95 milligrams, divided by 2 3 times, because 3 half-lives have passed. 1, 2, 3. I've got 11.9 milligrams remaining. Now here they want to know what the half-life is. Let's see. That decreases from 1.2 grams to 0.3 grams in 28 days. I started with 1.2 grams. I divided by 2 1 time, 2 times to get this much. So 2 half-lives have passed for 28 days. So then if 28 days is 2 half-lives, then 1 half-life is 14 days. Here, if I've got a half-life of 65 days, how long would it take to drop to 1/4 of the level? That is, if you initially start with an amount of 1 half-life, you'll have half as much. 2 half-lives is where you get 1/4 of as much. So 2 half-lives is 2 times 65. That's going to be 130 days. And 1/8 of its original level, let's divide by 2 again. That's 1/8 So that's 3 half-lives. So 3 times 65 is 195 days. These next 2 problems have to do with dosing, and we didn't cover any dosing in this particular chapter, but you have done dosing before with dimensional analysis, and that is all this is. They give you the units for dosage as microcuries per kilogram. And they want to know the answer in microcuries, and they give you the kilograms of the patient. You guys can do this. 4.2 microcuries per kilogram. If I have a 61 kilogram patient, I'm going to put that right here. So kilograms will cancel, and I will see how much remains in microcuries. That is a dose of 256.2 microcuries. So this is just like the problem that we did, except that in this case, now they're asking for millicuries, but they gave us dosage in microcuries, which is fun because see, they gave us the conversion between millicuries and microcuries. Other than that, it's dimensional analysis. You guys can do that. So we start with a dosage, 20 microcuries per kilogram of body weight. Put that down here. Microcuries per kilogram of body weight. And then we've got a 71 kilogram patient. Your numbers might be different than mine. And finally, they tell us that we've got 1 millicurie in 1,000 microcuries. We've got to put it there, so the microcuries will cancel. And if we do that, we can plug that into our trusty calculator and get our answer of 1.42 millicuries. So that is it. I hope this was helpful, guys. Have a great day.